this volume changes from initial to final, and this is always true. And when I say reversible, means all of a sudden that this one becomes minus P dV. And that's only for reversible. Okay? So this is when I say reversible, that's true. The external sign is gone. Same as an internal pressure. Then I have another kind of form that I can use, because if I do that on top, let's assume that this is an ideal gas. This pressure is depending on the volume change. Yes, it does. Not only that, I have a exact equation. Minus, what is the pressure? According to the ideal gas law, nRT divided by volume. That's the pressure, right? And then all I did is, and then I just copy down the rest of it. This is all I did. Initial and final. Can you see that? And so what this integral equation means, anything in this integral, I only see volume V as a variable, and then if anything the constant, I can take it out. And then the temperature is constant, so whole nRT is a constant value. So therefore, this one becomes minus nRT integration of 1 over V dV, initial volume, final volume. Do you remember I wrote it down this equation before the lecture? That's the equation, right? So what am I writing here is minus nRT natural log final volume. So this is that's an equation. If you're looking at any artwork on thermodynamics, this equation pops up everywhere. Okay, and it's so easy to try from here. Okay, so I like the summary on this because this is a beginning and I want to have a smaller start. So I want to write one more time, once again, okay? So this is the work irreversible is minus external times delta V, okay? Work reversible is minus nRT natural log final volume initial volume, and this is the isothermal HEC. And ideal gas that was given. There's another variant of this version. Can I write this equation this way? So sometimes are not clearly shown in any textbook. Can I write this way? Instead of writing the pressure ratio, can I write the inverse of pressure ratio? Yes, you can, right? Because you remember that temperature is constant. This is a constant, right? So the P initial, volume initial is same as P final, volume final. So the ratio is flipped when you do that. So sometimes actually expansion and they just talk about pressure changes, and you can use the kind of the variant of this equation. But this equation shows up like this. And in the first, I think the first class of this semester, I have chosen, you can choose a graph. Here I'm going to choose the two graphs. And my choice here is P external and P, and here's the volume. And that's my choice. Okay? Because if you're looking at this equation here, this is like almost like function dx that. So what this whole quantity means, which is work, has something to do with the area under the curve. Right? Same thing here. So I'm putting this one down, and this is a quantity that I want. And in the work irreversible, your external pressure has been constant throughout. So that's your case. Okay? And I am going to draw the internal pressure has been always bigger than that. And this one is coming down. And you will stop when your internal pressure, this is your internal pressure. Okay? And when this is coming down, and they will stop, and that will be your final volume. And that will be whatever you start with in your initial volume. And then what? This area under the curve, that's a work irreversible. Does it make sense? Emily, does it make sense?
Yeah.
Good. Can you, what am I doing in the, I want to do the reversible. Then what do I need to draw the external pressure, but this is same as internal pressure, right? So then what do? I'm just drawing the same thing over here, right? That's your external pressure, which is same as your internal pressure. When your internal pressure is same as your external pressure, this is a reversible case, and that's your external pressure. Same volume change from here to there. And the area under the curve, this one is work reversible. Same expansion, but work irreversible is bigger than work irreversible. If you know this one very well, there is a one sort of a minor mistake that I made here. I said area is work. Somebody might question, really? You told me work is positive or negative? I told you negative, right? The area is positive, right? So which is, just regardless of the sign, which is a more larger work should be done? Reversible case is a larger work. But like I said, -5 and -3, which is bigger? -3 is bigger in mathematical sense, right? The magnitude of -5 and magnitude of -3, -5 magnitude is larger magnitude, right? And all we carry is a magnitude, not in the numeric sense, right? So it's actually, you have to, if you don't, people do this trick all the time. If you do not care, if you do not worry about sign, just put a bracket there, which is an absolute negative. And then you don't have to worry about anything. It can be positive, it can be negative, all I care about the magnitude. And that's the answer it should be. Okay? I'd like to close that with one final comment, which is, I told you that reversible expansion is not real. Right? How can the internal pressure and external pressure is the same? Right? They cannot expand. They can go back and forth. So that's a true definition of reversible. So real expansion should happen. Look at me. This is a irreversible. Okay. I do like 20 irreversible expansion. How about this is a irreversible, right? It's a irreversible. This process will happen. If I do this 1,000 times, and that will be closer to the reversible work, right? So therefore, the reversible work is a reference point. You should think about it, not as a real process, but it's just good to know what is the maximum work for the expansion, and then we can get the work out of this. Okay, so that's the idea. Okay, the more you have more control about the external pressure, then it's getting closer to the real. Right? Okay, so one last comment before I move to the last chapter is going back to the original first law equation. My first law equation, let's go back to this. We just talked about this, right? Work is minus external pressure, volume change, internal volume, final volume. I can calculate that. What about measurement of the heat? Can I measure the heat? Yes, we can. Okay, we can measure the heat because that's a calorie that you put it in or put it out. But by doing so, all of a sudden that what we have now is we have a clue about what is the value for our state function change, right? So that is how they are related. And so for here, for this case, I'm going to say, let's just consider the constant volume. When your initial volume is same as final volume. Okay, so this is a special case for internal energy, makes my life extremely easy. So on the constant volume, you can say that delta V is 0. What's going to happen no matter what you do? If this upper bound and lower bound, lower bound and upper bound is the same number, I can guarantee this is 0, right? No matter what happened. No matter what happened, I can guarantee that's going to happen. They're going to be 0. And so therefore, on the constant volume, the equation up there coming down to delta U is Q plus 0. And then I'm going to have a little constraint, which is heat on the volume change. So the internal energy is same as heat supply on the constant volume. Okay, so constant volume. Have you heard about bomb calorimeter? Have you heard about this bomb calorimeter? Well, have you done the experiment actually? No? In the XChem, I don't know, 3, 2, 1? It was 1? Okay. So bomb calorimeter means essentially your bottle that you guys had, right? If you have a gas and just seal the cap, that's a bomb. There's no volume change, it's just fixed there. So whatever you do, and so if I have system that is fixed the volume, and then what people can do is the easy way for you to supply heat is just like your hair dryer. You supply the heating coil, you measure the current, how much current it flows, and measure the resistance, and there is a very well-known equation. So it's 100% conversion of electrical energy into the heat. So I exactly know how much of the heat am I getting. Okay? So then that exact amount of heat it will be used to measure the use for the increase in the internal energy. This is what they call the bomb calorimeter, which gives a convenience of I don't have to worry about expansion, which causes a complication. Okay? The more real system is under constant pressure, and that's what we are going to talk about. I guess the next segment. Okay, so if this one ever happens, if you supply the heat, which is this is a system, your heat is supplying, so you give out the heat to the system on the constant volume. You know what's going to happen to this system? You're the sealed container, you supply the heat, you put the Bunsen burner and you supply the heat. What's going to happen? Temperature. Temperature is going to change, right? Temperature is going to go up. So it is a natural kind of curiosity as a human being, as scientists. I supply the heat, there is a temperature change. Is it proportional? And yes, they are proportional, and they come up with a name called heat capacity. Okay? So it's a natural thing to consider. I put heat, And how much of the volume change, and the people decide to do it this way, the ratio as a heat at the top and the temperature at the bottom. So it's actually it's going to be other way around. How much heat do I need if I want 1 degree change? For water, that's 1 calorie, right? You remember that? 1 grams of water, 1 degree C increase, that's 1 calorie, and that's, I forgot the number, 4 point some joules.
4.8.
Yeah. Good for you. Anyway, so this is the idea of a heat capacity. So, I mean, I didn't put any kind of notation there, but that's the one. But what we are really dealing with is change in the temperature. Am I right? And this particular situation is constant volume. Right? And so therefore, this is a heat capacity of the constant volume. Because now we have described this heat capacity on the constant volume. So heat capacity on the constant volume. So this is a one important clue now, right? Okay. Well, one last equation to write before the break. So let's talk about heat capacity. So now I'm going back to the heat capacity now. And there are different heat capacities, and the heat capacity on the constant volume, right, should be changing the heat on the constant volume and changing the temperature. And this one is, what did I say about this one is on the constant volume, it is a change in the U, changing the temperature on the constant volume. So that's the one. And I'm going to write this, which is seemingly a lot easier form to write.